Okay, you have submitted homework 1 just a few minutes ago, and I'm going to give the solution to the grader today. I won't be grading the homework assignments, so don't get mad if points get taken off. I'm going to explain to the grader kind of my standard impression that a minor mistake should be -1 point. A more fundamental error and misunderstanding is maybe 2 or 3 points off, and it's cumulative. But then you should always get some points for attempting a homework problem, even if you have lots of consecutive errors along the way. So it's an art as much as a science, but if you think that you've had too many points taken off a homework assignment, if you've got concerns or gripes, you can come to me and I'll take a second look at what the grader's done. So let me know if you have any concerns about that. I'm hoping that in general your homework assignments will be graded with about a 1-week turnaround. So the second assignment is available to you now. It's due a week from today, so it should be submitted before class on Wednesday the 24th. And you can start those problems today based on the examples that we'll be going through. We're now moving from Chapter 7 of the textbook to Chapter 8. Hopefully, if you haven't got the book yet, it's on its way and going to arrive shortly. Are there any schedule or announcement related questions before we move into the new material? All right. So we've already looked at the Moody diagram a couple of times, and what we know about it is it's not convenient and it's not accurate because it relies on us taking a ruler and finding intersecting points. So that imprecision and interactive nature leaves us wanting something a little bit more precise and something that we can automate, that we could embed into a spreadsheet and do calculations in an iterative way. So we won't use the Moody diagram much, and instead we will turn to either the Colebrook equation when we want really high precision for calculating the Darcy-Weisbach friction factor F. In rare circumstances, we can use this expression that the friction factor is 64 divided by the Reynolds number, but that's only when conditions are laminar, and they usually won't be. The only times that conditions are laminar is maybe like in the middle of the night when most of the town is asleep and one person is opening up the faucet and getting a drink of water. In that rare case, maybe the water's flowing through a pipe at such a small velocity that conditions are laminar, but there's so little friction loss during that low flow condition that we don't really care what the F value is. And so you won't ever design the governing case using a friction factor with this 64 divided by the Reynolds number. Under most actual service conditions, you'll have to either use the Colebrook equation, which is tricky because it's implicit. And by implicit, what I mean is the unknown we're trying to solve for, the F value, you'll notice it's on the left-hand side of the equation and it's also on the right-hand side of the equation. And no amount of algebraic rearranging is going to allow us to isolate the F in that expression. So it's best to solve this equation either with a good calculator or using Excel. You can do trial and error, hand calculations, but it'll take you a long time. Probably more time than you want to invest in it. And by a good calculator, what I mean is, the kind that they don't sell anymore, unfortunately. The Casio calculator that you buy is not going to be convenient to solve the Colebrook equation. Maybe if you had some patience after 30 or 45 seconds, it would converge and solve for F. But the annoying thing is that you don't have a full keyboard on the Casio calculator, and so you can't type in like variables such as RE or F. Well, maybe F's on that keyboard, but it doesn't have the entire alphabet for assigning variables, and so I find the Casio a little bit cumbersome for solving the Colebrook equation, and I'll show you in an example today how to solve it using Microsoft Excel. If you want to, by the way, emulate one of these good calculators, there are programs in the App Store that you could install a good calculator on your phone, but then of course you can't use your phone during an exam. So, I mean, you could use it for calculations, and that's what I do. I use the Droid 48, which is an emulator of the HP 48 calculator, and it has all sorts of built-in matrices solving abilities. It'll solve financial functions. It'll integrate and differentiate equations. You could put in the Colebrook equation using actual variables as is found in the Colebrook equation, and you could solve for the unknown, even though it's implicit. By the way, remember that K sub S means the equivalent sand roughness. Some texts use epsilon, some texts use K sub S for that. That's the way of representing the roughness of the material. So the two terms inside of this logarithmic function, one of the terms has to do with the relative roughness, and the other term has to do with the flow conditions, because the Reynolds number is in the denominator there. And so there's two main things that determines what the friction factor is. Two separately influencing factors. One is the pipe materials relative to the diameter of the pipe. So that's the first term, is what the pipe is made out of. And then the second term has to do with what is the velocity of flow through the pipe. And that's captured in the Reynolds number. So we'll look at how those two different factors, sometimes in some conditions, one will dominate over the other. Sometimes they both contribute equally. But it has to tie back into the fully turbulent flow versus the laminar conditions that we've talked about a little bit before, the thickness of the boundary layer relative to the equivalent sand roughness of the pipe material. So here's a table, another table of the material properties. I've showed you one from our textbook in a previous class meeting. I think that this one's from the fluid mechanics textbook that's published by Wiley. It's the same values, but just expressed in terms of either millimeters or inches. And remember that each of these terms inside the logarithm would be dimensionless. And so you need to have the diameter of the pipe expressed in the same units as the relative roughness. And then both Reynolds number is unitless and F value is unitless. And so the second term would also be unitless. So we need to pay special attention to making sure that we cancel out the units, because inside the logarithm it should be a unitless expression. So we want to know what is the friction factor for a pipe under certain flow conditions. And just to demonstrate how we could use Microsoft Excel to solve it, feel free to get out your computer if you've got one today. Like if you have your laptop here, you can follow along. And if you don't, that's okay. You could maybe go through it later, and the video will be posted on YouTube. But let's say that we have a pipe that's 136 millimeters in diameter, and it's galvanized iron. And so if we go back to that equivalent sand roughness table, we would find that for galvanized iron, the K sub S is 0.15 millimeters. And then we want to know what's the friction factor F when we have a flow of 200 liters per second going through that pipe. So there are certain things that we're going to start off on the whiteboard, namely calculating the Reynolds number, and then I'll switch over to Excel after that. But just to set things up, set the stage, the pipe diameter is 136 millimeters. K sub S is 0.15 millimeters. Let's calculate the area of the pipe, pi d squared divided by 4. So pi times 0.136 meters squared divided by 4. So the area of the pipe is 0.01453 square meters. And then the flow velocity, Q, if it says it's 200 liters per second, that's the same thing as 0.2 cubic meters per second. Because what we know is that there's 1,000 liters in a cubic meter. So if we divide 200 liters per second by 1,000 liters per cubic meter, that gives us 0.2 cubic meters per second. How do we calculate the velocity of flow through the pipe? V equals, good, Q divided by A. That's just the continuity relationship. Flow rate is velocity times cross-sectional area. So here it's 0.2 cubic meters per second divided by our calculated pipe cross-section area, 0.01453 square meters. And the flow velocity is 13.77 meters per second. So water's really zipping through this pipe at a really high velocity. This is an extreme case. We wouldn't typically see water going that fast through a pipe. But in this hypothetical, it is. So what would be the Reynolds number for these conditions? Reynolds number is the velocity times diameter divided by the kinematic viscosity. And it says here, we're just talking about standard temperature water with a kinematic viscosity of 1 times 10 to the minus 6th meters squared per second. So we have our velocity of 13.77 meters per second, our pipe diameter of 0.136 meters, and the kinematic viscosity of 1 times 10 to the minus 6th meters squared per second. All right, so our Reynolds number is 1,872,413. All right, so with that in my back pocket, I'm going to switch to Excel now, and we're going to try and find out if we know the pipe diameter, D, that's a constant. We can substitute D in. We can substitute in K sub S, that's known. The only unknown in this equation is F. It's on the left-hand side, it's on the right-hand side, and it's kind of embedded. It's embedded under a square root symbol in the denominator. On the right side, it's also inside of the logarithm. So let's see how we could use Excel to solve this one. And I'm going to copy the equation so that I can paste it into my Excel workbook. So I'm just going to paste that so we can look at it as we set things up. So what do we know? We know the pipe's K sub S is 0.15 millimeters. We know the diameter of the pipe is 136 millimeters. And we know the Reynolds number is 1.872 times 10 to the 6th. So rather than typing in the whole number, you'll notice what I did is I just said 1.872 capital E6. And then when I type enter, if I go back and look, it's basically translating that E6. It knows that it means times 10 to the 6th. All right, and I guess, if I wanted to have all my precision in there, I bothered calculating it. Let me say 413. All right, so now that's the full Reynolds number with all of its precision. I'm going to start with a guess value of F. And just so things aren't confusing, I'll do the lowercase there. So I'm going to start with a bunch of guesses of F. And F typically starts as low as 0.008 and goes through 0.0038. So I don't know yet what the F value is, so let me just put them all in there. And my approach is I'm going to calculate the left-hand side of the equation and the right-hand side of the equation and then look for the difference. When the difference is 0, that tells me I have the right F value. So I'm going to have the left-hand side of the equation, the right-hand side of the equation, and then calculate the difference between the two. So by left-hand side, what I mean is I'm going to have 1 divided by the square root of F. So 1 divided by square root of F. All right, and if I double-click here in this green box that's at the lower right-hand side, then it automatically drags it down through the entire list. So that's the left-hand side of the equation. 1 divided by the square root of F. The right-hand side of the equation, I'm going to be referencing K sub S, referencing D, referencing the Reynolds number. So I'm going to click on these cell locations as I assemble that formula. Another way that you could do it, maybe this is a trick that you already know, maybe not. Look up here at the top left. You see B1 is called B1, but I could also assign it another name. Like I could say, I'm going to also call that KS. So now I can type KS in a formula and it knows to look in cell B1. Or I could rename B2. I could just call that D. I could rename B3, I could rename it RE. So you can assign a secondary variable to cell locations. And so I'll use that as I set up the right-hand side. So equals -2 times the log of KS. See, I don't even have to click in the cell location. Divided by 3.7 times D. Okay. So is everybody comfortable so far with how I've typed in this first term? Okay, that's not how I'm typically going to type it in, though. It's a little bit faster if you type it in this way instead. K sub s divided by 3.7 divided by d. So it saves me from having to put in the parentheses if I just say divided by 3.7 and then divide it by d. And it's the same thing as if you had put in those parentheses. So don't let it throw you for a loop. Plus 2.51 divided by RE divided by the F value. All right, close parentheses. So the right-hand side of the equation is 7.01. I'm sorry, 6.66.
Do you need to square root the F value?
Yes, I do. Thank you for catching that. Good catch. All right, square root. So now I can distribute that down, and all of the references here to like K sub s and D and RE, those are all anchored, the same as if we'd use dollar signs when referencing B1, B2, and B3. So I double click here, and you see how the right-hand side equation is changing, and then I want to find the difference between the two. And so whichever row has the difference closest to 0 is telling me what the F value is pretty close to. So the F value is about 0.02. About is not generally good enough. We want it to know exactly what the F value is. So how could we find out exactly what the F value is? What's our objective here? It's for the difference to be equal to 0. So how can we find like precisely what is the F value?
Goal seek.
Yeah, goal seek. And so you're right. What would be our objective in applying goal seek? We want this to be 0 by changing the guess of the F value. So I'll go here to the data tab, what if analysis, goal seek, and what we're going to do in goal seek is we want set the difference to be 0 by changing the F value, and it's going to play around with a bunch of different guesses for F until it finds the one where the left-hand side and the right-hand side truly are equal. All right, so the actual F value is 0.020266621. So what we'd actually use for calculations is we'd say the F value is 0.0203. So now we have a good calculation of the F value. The Colebrook equation is valid across the entire range of possible pipe diameters. It's valid across the entire range of possible flow velocities. So it's an equation that we can use anytime that we don't mind going through this tedious process to calculate the F value. Because it's implicit, it's a trial and error approach. But if we're using the computer for hydraulic calculations like we will with water gems, it will use Colebrook equation in the background, and we don't have to think about the fact that it's implicit and iterative and time consuming, because it won't feel time consuming. It'll just do it automatically. So any questions about this illustration on how to calculate the F value of the Colebrook equation? So I think this is one of your 7 homework problems that you've got for next week, is to do the same thing. Use the Colebrook equation for a couple of different pipe diameters. So that's easy enough. I'm happy to tell you that there's an even simpler way to calculate the F value pretty accurately, and that is the Jain equation. The Jain equation is it's not implicit. It can calculate the f value directly. You'll notice that the f value is only on the left-hand side of the equation here. But it's just an approximation, and it's only valid under a range of circumstances that generally apply, but sometimes you could conceivably be outside the range of the relative roughness being between 10 to the minus 6th and 10 to the minus 2. So if you had a really small diameter pipe, like very, very small diameter pipe, the Jain equation maybe would be outside of that range. Or if you have a Reynolds number that is below 5,000 or more than 10 to the 8th, then Jain equation also doesn't apply. But most of the time, we're okay with the Jain equation. So you'll notice it looks in some ways similar to the Colebrook equation because we have the same two terms inside of the logarithm. Although this is a natural logarithm, so base e, we still have a relative roughness term inside of there, and then we've got a Reynolds number term which relates to the flow velocity. So both of those things contribute to finding out what's the f value. The pipe material compared to the pipe diameter is part of it, and also part of it is the flow conditions. And so f could change even for the same pipe. So let's say you've got a cast iron pipe. If you have cast iron and water is flowing through it slowly, you'll have one f value. But cast iron with water flowing through it at a high velocity, you'll have a different f value because those would be two separate Reynolds number. Even though the pipe diameter is the same and the pipe material is the same, different flow velocities will give you different f values. And that's actually part of why we go to the trouble of using the Darcy-Weisbach equation, is it's the most accurate way to estimate pipe friction. It's more accurate than other techniques I'll show you later on. Like we could use the Manning's equation to calculate head loss due to pipe friction through a enclosed pipe, but it's not accurate for closed conduit flow. There is the Hazen-Williams equation, which is convenient, but it's less accurate. So this is the most accurate equation, the Darcy-Weisbach equation is, because it's adaptive to the flow conditions. The f value, the way that you estimate friction, is sensitive to flow conditions. And a lot of the other methods aren't. So I'd like to pause for a moment and give you a chance to run the numbers on this one. We've calculated for these same roughness, diameter, and Reynolds number. We calculated what was the f value according to Colebrook, but I'd like you to apply the Jain equation. And you can do this one by hand. You don't necessarily need a spreadsheet for this. But just substitute it into the Jain equation and see what you get for f, and we'll see how closely it approximates. All right, so when we were solving the Colebrook equation, we got the pipe area, Reynolds number, velocity, and so on. And we found that the f value was 0.0203. That was the Colebrook answer for f. The Jain approximation, if we substitute in the relative roughness in the same units as pipe diameter, and we put in the Reynolds number to the 0.9 power down the denominator there and calculate it, we get the same thing. In this case, also 0.0203. So did anybody else confirm that? Yep. Okay. So in this case, the Jain this is right in the middle of the range of values that the Jain equation is okay to use, and it's going to align perfectly well with the Colebrook equation. And so this semester, you can use the Jain equation unless I specifically tell you to use the Colebrook. And so, like on the homework assignment, you have a problem where I say to use the Colebrook equation. There could be a quiz or exam problem where I ask you to use Colebrook. But otherwise, for all the problem solving we do, feel free to use the Jain equation instead. Are there any questions before we move on? The Blasius equation is another one that I suppose it's good to be informed about. It's valid for Reynolds numbers up to 100,000. but it doesn't have sufficient flexibility that we won't use it very often. The Colebrook equation coincides with the same range that the Blasius equation does, but I guess it's good to know. Okay, so sometimes you have to size a pipe. You have to figure out how big the diameter should be in order to accommodate a desired flow rate. Let's say that we have an elevated tank and you have water flowing through a pipe to get to a building, and you don't know how big the pipe should be in order to get a flow rate that you want to have there. Let's say you know the pressure you want to have, and you know the flow rate that you'd like to achieve, but you don't know how large the pipe needs to be in order to have it happen. So we're going to talk today about how we can use the Darcy-Weisbach equation and calculating F values to estimate the pipe size that's required. In an example problem like this, you might be able to calculate the head loss with some precision. In this illustration, we know the head loss because it would be the difference in the starting energy and the finishing energy. And so if we have an elevated tank where the water is motionless inside of this tank, but we know the altitude that it's elevated at, the Z, and here at the interface of the air and the water, we know the pressure is 0, gauge pressure. And then we know in the building the pressure that's desired and the elevation of the building. We can calculate how much head loss there is. This is just rearranging the energy equation to solve for H sub F. And the slide makes the point that the velocity term is often omitted from this because in some cases the velocity in both locations is equal, and in other cases the velocity is negligible because the water is moving so slowly. So oftentimes they'll just leave it out entirely. Although it's okay to include it, it just sometimes won't make a difference. So head loss can be known or expected for certain conditions, and you know the flow rate you want to have going to the destination, and it could be that you know that because you've done some estimation of how much water people need. You know, if you've got 10,000 people in a neighborhood and you know how much water they're going to use for watering the grass, for washing dishes, for drinking, for doing laundry. You know, you can do a pretty comprehensive analysis and look at peaking factors and human behavior and time patterns and how it varies throughout the day and just determine what's the peak flow rate that you need to be able to provide. And so you'll have to size the pipe, you'll design it to determine the diameter that will give you an acceptable flow rate and for the head loss that's driving the flow through the pipe. So that process is iterative, and that brings up the difference between design and analysis. In the case of analysis, usually it's not a process that you have to do trial and error on, but in the case of design, you don't know what the answer is at the beginning, like the required size of something. Oftentimes in design there's multiple constraints that you're trying to balance and trying to minimize the cost of something. But in this case, what I'm trying to highlight is that in design, frequently we'll have to do multiple calculations, like determine a first guess, adjust it, calculate again, adjust further, calculate again, and that's especially true when friction factor is involved. So you've seen this equation before. This is the Darcy-Weisbach equation for estimating head loss due to pipe friction. So we know that it depends on friction factor, the pipe length, the velocity through the flow, the velocity of flow through the pipe, its diameter, and so on. And if you rearrange this equation for the unknown being the pipe diameter, and if we have a circular pipe where the velocity for a certain flow rate is determined by assuming the cross-sectional area is d squared divided by 4, pi d squared divided by 4. You know, if we rearrange it and solve for the diameter for circular pipe geometry, then here's what we are ending up with. So this is like what diameter would be needed if you knew how long the pipe was going to be, if you knew what the flow rate through the pipe is, if you know what head loss is driving flow through the pipe, You can think of H sub F as how much energy is being exerted as the water flows through the pipe. And then it also depends on the friction factor. So it seems easy enough. You know, D is only on the left-hand side of the equation, so it's not that implicit equation that we were talking about earlier. But there is something that makes this process tricky. And that is, we don't know what diameter of pipe is needed until we know what the friction factor is. But what does the friction factor depend on? Do you remember what in the Jain equation, what are some of the terms that friction factor depends on? Well, friction factor depends on flow conditions and pipe diameter. So we're saying we're calculating the pipe diameter, and the pipe diameter depends on the friction factor, but the friction factor depends on the pipe diameter. So the two variables are related. F depends on D, and D depends on F. So it isn't as independent as we would like. So we can't calculate D until we know F, and we don't know F until we know D. So it's like a stalemate, right? When two people with pistols are aiming at each other, it's a standoff. So what we have to do to overcome that is we just have to start with a guess. Like, we don't know necessarily what the F value is, but we can guess a typical F value, and then we'd say, well, what would the pipe diameter be if it was just kind of a typical value for the friction factor? And then you calculate what diameter would be required, and then you say, all right, well, with this first round of calculations done, I got a certain diameter, and if it's that diameter, then the water would be flowing through the pipe at a certain velocity, and then we can maybe improve on our initial guess of the F value. So that's what we're going to do in this iterative approach that's the most accurate to determine the pipe diameter that's needed, is go through the steps of, first, assume an F value, just guess something between the likely range of 0.008 and 0.038. Maybe somewhere in the middle, like 0.02. We'll start with a guess, and then we'll solve for the diameter based on that guess, and then we'll calculate what's the Reynolds number based on the assumed F value, and then the consequentially following diameter. We determine the relative roughness, update the F value with this Reynolds number and relative roughness using either the Colebrook equation or the Jain equation. And then we go through the cycle again. Once we've got a new F value, we can calculate an improved guess of the diameter. And eventually, if we go through the cycle a couple of times, things will stop changing. And that's the indicator to us that we don't have to do any more iterations, is what's called convergence. When the solution is stable, it's not making any further adjustments with subsequent iterations. So I've put a template file on Blackboard. If you want to follow along in this example that we're going to solve next, there's a blank template file on Blackboard that has some of the formulas already filled in. So we're going to look at this case of, what if we had a pipe, and it's like a big main pipeline where we know the pressure there, and we have a lateral pipe coming off of it. So maybe this lateral pipe is going to a building from the main pipeline. This lateral pipe is 40 meters long, and we know that it's made out of cast iron, so that gives us the relative roughness, the equivalent sand roughness. And we want to have 300 liters per second going through there, and then the driving head is 45 meters. So we know that because we know the pressure in the pipeline, and we know that when the water comes out of this 40-meter pipe, it's discharging into the atmosphere. So just for whatever reason, we know H sub F. And the most simple way that we'd know it is if we knew the difference in pressure between the beginning and the end of the pipe. So we want to know what is the pipe diameter that's needed. And so the process I'm going to go through is I'll start with an assumed value of F and calculate what would be the resulting diameter. Then I will calculate, based on that first guess of the diameter, what is the Reynolds number and equivalent roughness. And then I'll refine my guess of the diameter by improving the F value estimate. And I'll just keep repeating that process a couple of times until it converges. So the The template file that you should, there's only one, I think, in the folder online. It is pipe diameter needed. So we've got our problem statement here at the top. The length is 40 meters, the flow rate, and so on. So let's start filling in this spreadsheet. We know that the flow rate needs to be in cubic meters per second. So I'm going to type in for this one, it's 0.3 cubic meters per second. So 0.3 cubic meters per second. The K sub S is 0.26 millimeters. The length of the pipe is 40 meters. G is 9.81 meters per second squared. The head loss that's driving the flow through the pipe, was it 45 meters? And then the kinematic viscosity of water is 1 minus 6 meters squared per second. Okay, for the first iteration, we're just going to assume an F value. And so I'll use kind of an initial guess of 0.02 as the guess of the F value. And now I'm going to use this to find out what diameter would be required if this was my F value. So it is 8 times L times Q squared times F, that's also in the numerator, divided by H sub F times G times pi squared. And then all of that is to the power of 0.2. So 1/5 power would be to the power of 0.2. Looks like I've forgotten something. Let's see. Did I forget a parenthesis somewhere?
I think you had extra parentheses.
In any case, it seems like it's figured it out. That is the diameter that would be applicable for this guess value of F. Let me just check if I had a guess value of 0.008. No. I've got an error somewhere. When in doubt, throw it out. Just start over completely. So equals 8 times L times Q squared times F divided by H sub F times G times, I'm going to just type in 9.81 in case that was the issue, squared. And then all of that, one more parentheses, now all of that to the power of 0.2. Yes, all right. The K sub S value, I wrote it 0.26 millimeters, but I need to write it in terms of meters. So I'm going to also do divided by 1,000, because now that would put it in terms of meters. So we need to make note, check the units for consistency. Because that is going to come into play a little bit later. Okay, so if we have that middle ground F value of 0.02, then what would be the flow conditions that would correspond to that? So the flow rate would be the velocity multiplied by, well, the velocity is given. It is the 0.3. So let me just refer back up here to the flow rate. The cross-sectional area for this pipe diameter would be 3.14159 pi times, hold on a second, in here. I typed in pi wrong. I typed in G. Pi is 3.14, right? You guys need to keep me honest. 3.14 159. I'm definitely rusty today. All right. So the area is pi 3.14159. Pi times d squared divided by 4. And then the velocity is q divided by the area. Okay, so I've got the water flowing through the pipe at some velocity. And now we can calculate the Reynolds number if the flow is that velocity. It is the velocity times the pipe diameter that we've calculated divided by the kinematic viscosity. Since I'm always going to be referring up here to this top part for the kinematic viscosity, I'm going to anchor that reference, but I won't anchor the others because I'm going to do multiple iterations and I want to be able to just copy and paste in subsequent iterations. So what would be the new F value under those flow conditions? So the new F value, we can use the Jain equation for that. Let me grab the Jain equation here and paste it into the function. So the new F value is 1.325 divided by the ln of k sub s divided by 3.7 divided by d plus 5.74 divided by the Reynolds number to the power of 0.9. And then all of that is squared. So I have a new improved guess of the F value. And so how much did it change from the previous guess? The percent difference is the new one minus the old one divided by the new one times 100. So it changed 9.31%. All right, so now in iteration 2, what I'm going to do is I'm going to use this improved F value that I've just calculated, and I want the diameter to be calculated using this equation, but with the new F value. So what I can do, since this is based on, I should probably anchor some references if I want to be able to copy it down, because I always want it to look at, for example, the Q, the L, the G. So if I do the F4 and make all those references absolute that need to stay absolute, then I can copy this, Control C, and then paste it here. And what it's doing is it's calculating the diameter with the new F value, but with all of the constant pipe length, head loss, G values, and so on. So you'll notice that the diameter that we calculated the first time said 0.16 meters. Now it's 0.17. So the nice thing that we can do at this point is just copy and paste. I can copy the values for the flow rates and calculating the Reynolds number, paste that down here, maybe. Need to be absolute reference for the Q. Copy and paste. And then we can calculate the new F value by just copying the formula from before and pasting it here. And we are out of time. It's 11:50, so when we get together in class on Wednesday, we're going to continue this example just because I think it's important for you to see how this gets to eventually converging. So you can get started on the Jain equation and Colebrook equation part of the homework. And remember that the technical conference tomorrow, it'd be a really great opportunity for you, so I'd encourage you to attend. So I'll see you in class on Friday.